So the first question involved a buffer. So we have a buffer of 150 milliliters of 0.35 molar chloroacetic acid and 0.23 molar sodium chloroacetate. What's the pH after 0.02 moles of HCl are added to the buffer? And it gives us the Ka of the weak acid. So since we're adding a strong acid to the buffer, it's going to react with the weak base, aka the chloroacetate, and it's going to produce more chloroacetic acid. So since this is a buffer, we'll be using the Henderson-Hasselbalch equation. So we need to know, in order to solve this problem, we need to know the concentration of chloroacetic acid and chloroacetate that remains after we've added the 0.02 moles of HCl. So since we're adding moles of HCl, the pH should be less than the pKa of the acid. So we found the pKa is 2.89. We need to find the moles of the weak acid, moles of the weak base, and we have the moles of the strong acid H3O+. Now for the buffer reaction, again, we're going to react the weak base with the strong acid to make more weak acid. So it looks something like this when we set up our ice table. So the conjugate base reacts with the strong acid and forms weak acid. So you always subtract the lesser one from the greater one, and as long as the moles of strong acid or moles of strong base is the lesser one, your buffer is intact. Whenever you notice that the moles of strong acid or the moles of strong base are greater than the moles of weak acid or base, then your buffer has been destroyed, and you simply see how much of the moles of the strong acid or base remains to calculate the pH. But here we're okay. So we subtract 0.02 moles from the weak base, and we form 0.02 moles of weak acid. So at equilibrium, we have the moles of these. So now that we have the moles of the weak acid and its conjugate base, we can find the new concentration, plug it in, and we get a pH of 2.19. So this makes sense. Since we added a strong acid, the pH is going to decrease. Since there's more moles of weak acid than weak base, our pH should be less than the pKa. So here again, we have the same buffer, but instead of adding a strong acid, we're adding a strong base. So we add 1.4 grams of sodium hydroxide. What will be the pH of this buffer? So again, we're going to be using the Henderson-Hasselbalch equation. We need to know the concentration of weak acid and its conjugate base that remains after we've added the strong base. Again, we're going to need the pKa. So here we calculate the initial moles of weak acid, initial moles of weak base, and we find our moles of hydroxide, mass divided by molar mass. So we set up our ice table. Notice how it's kind of flipped. Here the weak acid reacts with the strong base to form conjugate base of the weak acid. Again, notice that the moles of strong base is less than the moles of weak acid, so our buffer is intact. So we're going to subtract the moles of strong base from the moles of weak acid and add them to the moles of the conjugate base. So now we get our new moles of weak acid and conjugate base. We calculate the concentration. We can find the new pH. So here it's 3.49. Again, since we're adding a base, pH should increase. Secondly, since the moles of weak base are greater than the moles of weak acid, our pH should be above the pKa. So this has a pH of 3.49. Okay. Now the previous two problems involved just a buffer, calculating the pH of a buffer after we added a strong acid or strong base. The next few problems deal with titration. So here we want to calculate, or we're doing a titration involving 35 milliliters of a 0.27 molar perchloric acid solution titrated with 0.15 molar LiOH. So since we have a strong acid and a strong base, this is going to be a strong acid-base titration. And we want to determine the pH at the following different points of this titration. So first we want to look at what's the initial pH, what's the pH after we add 45 milliliters of LiOH, and what's the pH at the equivalence point. So for the first one, what's the pH before any base is added, we simply just take the concentration of acid and take the negative log of that. So the negative log of 0.27 is 0.57. So the pH of this 0.27 molar solution is 0.57 before any base, strong base, has been added. Next, we want to know what's the pH after we added 45 milliliters of this 0.15 molar LiOH solution. So here what we need to do is first determine the moles of strong acid that we have, the moles of strong base, and also remember that the volume is additive. So we have 35 milliliters of acid, we have 45 milliliters of strong base. So the total volume of this solution is 80 milliliters. And that's important when we want to calculate the new concentration of hydronium or hydroxide ions. So now for the strong acid, strong base titration, this is the reacting equation, if we want to call it that, or the net ionic equation. H plus OH minus, or H plus and H3O plus are the same, so you can use either one. Plus OH minus gives us H2O. So initially we have moles of H plus, we have moles of hydroxide. You always subtract the lesser one from the greater one. So here the moles of acid are greater than the moles of hydroxide. So we subtract because all the hydroxide is going to react with all the strong acid. And so we get to see how much strong acid is left over. So this is the moles of strong acid after we've added our 45 milliliters of this lithium hydroxide solution. We know the new volume is 80 milliliters, so we can calculate the new concentration of hydronium ions. Now we can take the pH by taking the negative log, and we get a pH of 1.47. So that's the pH after we've added 45 milliliters of this lithium hydroxide solution. Then lastly, at the equivalence point, since this is a strong acid and strong base, at the equivalence point, the pH is always 7. There's no calculation you need to do here. You just need to remember when you have a strong acid and strong base titration, the equivalence point is always at a pH of 7. Moving to the next example. So here, I've divided this question. It had 3 parts to it. It takes a little bit to work out each part, so I'm doing one part on each slide. So it's an A, B, and C. Here we do a titration, but we're using 25 milliliters of cyanic acid at 0.18 molar cyanic acid, and we're titrating it with 0.25 molar sodium hydroxide. Determine the pH at the following points in the titration. So here we have a weak acid and a strong base. And so we want to first determine the pH before we add any base to the solution. And so the way we're going to do this is very similar to what we did when we were calculating the pH of a weak acid solution. We're going to set up our equilibrium equation. We have the initial concentration of weak acid. We have the change. It's very similar to what we did in calculating the pH of a weak acid solution. Equilibrium. Now here, because Ka is a lot smaller than the initial concentration, we can ignore the minus X. and we can solve for x. And so we get the initial pH to be 2.1. So anytime you're looking for the initial pH of a weak acid strong base titration, you just solve it the same way that you would solve for calculating the pH of any weak acid solution. So we use the ice table, solve for the hydronium ion concentration, and then calculate pH. So the next one is we want to determine the pH after 12 milliliters of sodium hydroxide is added. So again, our equation is this. So first what we need to do is to determine, how many moles of weak acid we start with, how many moles of strong base we start with. So over here I'm going to calculate the moles of weak acid. And I'm going to calculate the moles of strong base. So now when you look at this, you'll notice that the moles of strong base are less than the moles of weak acid. Therefore, that tells us that this is going to be in the buffer region of this weak acid strong base titration. And so for the buffer region, we need the pKa because we're going to be using the Henderson-Hasselbalch equation. And again, the way I know it's in the buffer region is because the moles of strong base is less than the moles of a weak acid. So we're going to set up our ice table. So the change is all the strong base is going to react with the weak acid to form weak base. And so at equilibrium, we get so these are the moles of weak acid and moles of weak base that remain once we have added the 12 milliliters of sodium hydroxide. And so now we need to determine the total volume, which is going to be 25 plus 12. And we can find the concentration of weak acid and weak base. So now we know the concentrations of weak acid and weak base. We know the pKa. So we can calculate the pH after we've added 12 milliliters of solution. Again, it's the concentration of weak base over the concentration of weak acid. And since the concentration of weak base is greater than weak acid, our answer should be above the pKa. And we get about 2.55. And so the last one that we're going to do is what's the pH after we add 19 milliliters of sodium hydroxide. So again, we need to find the moles of weak acid, which is the same as what we found initially on the previous question. And we need to find the moles of strong base that we have now. And we get 0.00475. So notice here that the moles of strong base is greater than the moles of weak acid. So this means that we're beyond the equivalence point of this acid-base reaction. So all we need to do is to see how much or how many moles of hydroxide are in excess, and then we can determine the new volume and get the new concentration of hydroxide. So again, since the moles of hydroxide are greater than the moles of weak acid, we've exceeded the equivalence point of this acid-base reaction. So here's the moles of hydroxide that are left over, excess the total volume is going to be 25 plus 19, which equals, what is that, 44. So that's the new volume of the solution. Now we can calculate the concentration of hydroxide. Now that we have the concentration of hydroxide, we can calculate the pOH. We get 2.25, and then we can calculate the pH. We get 11.75. So again, the way I knew that the to use this process rather than the one in part B is because the moles of hydroxide are greater than the moles of weak acid. So that means there's an excess of hydroxide left over. So we found the moles of hydroxide that remained, divided by the new volume, and we get the concentration of hydroxide. Then we can calculate the pOH and the pH. So we looked at every different point for a weak acid strong base titration, except for how do we calculate the pH at the equivalence point, and that's something that we'll look at in the next session in one of the problems. Okay, just one clarification. In the previous problem B, I made a typo. So the correct answer is not 2.55. So when we do the log of 0.08108 divided by the concentration of weak acid, since the concentration of weak base is greater than the concentration of weak acid, our pH should be greater than the pKa. So when we do this, we get 3.46 plus 0.301. And so when you add these two together, you get a pH of 3.76. So that's the pH after we've added 12 milliliters of sodium hydroxide. So make sure you make that correction in the problem. So again, the correct pH for part B is 3.76. On that note, that's all for this session. Until next time, Dr. Armand signing off.